I'm super excited to present a project that I'm very passionate about. It's a project that I did as part of my studies. I did my bachelor in computer science here at ZHAW. And this is actually a project that I did as part of those studies. I did it together with a fellow student, so I was not on my own. And I also did it in cooperation with the Institute of Embedded Systems. That's actually the institute where I work right now as a research assistant. So this project kind of got me close to the institute and showed me all the amazing potential, resources, and know-how that was available at the institute, which is why I eventually started working there. So now that you have a little bit of an idea of who I am or how I got to the institute and now I would like to show you what I am going to present. So just to give you an idea. So this ground speed measuring system is actually part of a race car. And we tried to develop a system that was capable of measuring as accurate as possible the velocity over the ground of a race car. So I will quickly give you an idea of where this project is located, how we could use the system, or what was the idea behind the system. I will go into a few details regarding the system requirements that we had to consider. And then I will get to the fun part that I'm super passionate about, and I will try to explain to you the measurement concept which we had in mind and which we wanted to implement in order to come up with a solution for measuring the ground speed of this race car. I'll show you the most important results, and I will finish with what we've learned from the project and how we could continue it. So this whole project was actually centered in the context of the Formula Student ZHAW race team. So they have their own race car and they are trying to participate in races all over the world. And what we did, or what our part was to make the car also capable of autonomously driving. So the car currently needs a driver, but there are also competitions where autonomous race cars compete. So we were trying to put together a system piece by piece to make the current car self-driving. And our goal was to measure the speed over the ground, because this is essential for an autonomously driving vehicle to have a precise idea of the velocity over ground. And you can measure velocity in lots of different ways. You could just put an encoder to each wheel and you would have an idea of how fast you're going. And that's fine. But we wanted to be slightly more accurate in order to, for example, also detect if the car were to lose traction. So if one or multiple wheels started to slip, because a sophisticated controller could then, with a good input, could also give adjusted signals to each wheel in order to, again, get traction on the ground and to make more precise movements while autonomously driving. So especially when cornering or when taking turns, if we always have traction on the ground, then we can be sure that our car exactly follows the path that we were planning. So that's why we actually want to measure the ground speed. And we can do this, as I mentioned, with the help of lots of different sensors. And what we wanted to do is we wanted to take a few sensors, 2 at least, and combine the inputs from those sensors to one more accurate, improved signal for the velocity of the car. So this idea is called sensor fusion. It's not new, but we wanted to develop it for our race car. And so the idea is we want to have an accurate measurement for the velocity. We wanted to use it mostly in our Formula Student race car, but of course you could also use it in other autonomously driving vehicles or in other scenarios where you would want to do slip control and just have an accurate idea of the ground speed. So I'm now jumping into the concept of how we wanted to measure this velocity. this slide will give you a short overview, and all the following slides will have pretty pictures and graphs to explain all the ideas that I'm summarizing on this slide to give you an overview. So we have two sensors in the car. The first one is an IMU. This is an inertial measurement unit, which consists actually of three sensors in one. So it measures acceleration, it measures the rate of rotation, and it also is capable of finding the magnetic north pole, so it's also a magnetometer. And this thing, this IMU, is mostly used to figure out how an object, or the sensor which is attached to the object, how it's located in space. So we can measure the attitude of an object. And this is super important once we want to use the second signal that we get from the GPS. So the GPS delivers us directly a velocity signal. We don't really care about the position. We could actually use the waypoints and the time in between when those waypoints were measured in order to get the velocity. But it turns out the GPS can actually directly deliver a velocity signal, which is based on the Doppler effect. So this is surprisingly accurate, and that's why we went for the GPS. So we take the velocity from the GPS. And we combine these two sensors in a process that I will now explain to you. So the IMU, as I mentioned, we want to use it to figure out the orientation of our car in space. So we do everything in 3 dimensions at first, and only in the very, very last step, we'll reduce this to a 2-dimensional velocity of the car on its plane. And in order to figure out where this car is located, we want to figure out 2 vectors that will give us a relationship between a reference frame that is attached to our globe, an inertial frame or a fixed reference frame. It is relative, like its axes are pointing north, east, and up. And we want to figure out how this is related to the reference frame of our car. So for that, we figure out a gravity vector that points down, a vector that points north, and then we combine this to get the attitude. Once we have that, we try to figure out the true acceleration of the car, and then we combine this true acceleration with the velocity of the GPS that we also have to rotate. So now I'll show you a bunch of pictures to make this more clear. Also, as a small overview, so on the left-hand side, you can see the inputs that we have, the 2 sensors. The top one is the inertial measurement unit, and the bottom one is the GPS, from which we are just taking the velocity signal. And we need to fuse this data together, which we're doing with 2 separate Kalman filters. So one Kalman filter is responsible for the attitude, which is represented by a quaternion, which is actually a super neat but slightly unintuitive mathematical way for representing the orientation of an object in 3-dimensional space. We want to get the linear acceleration, so that the true acceleration from the accelerometer. And we want to combine this in a second Kalman filter with the velocity signal from the GPS in order to get the speed over the ground of the race car. So let's see how we do this with the most important pre-processing steps. So I mentioned the gravity vector. We can use the accelerometer to detect the gravity that is pointing down. So we actually have one vector that's super easy to work with. And we have a second vector that's slightly more complicated, but also very useful. It's the vector that points to the magnetic north pole. This slightly varies depending on where you are located on the globe, so you have to look up properties for where you want to use the system. But once you have this figured out, you can combine these 2 vectors, and you will figure out how your car is located on the globe. So that's actually the relationship between a body frame with axes x, y, z. So the y-axis will become important because that's the forward-facing axis of the car. And we want to know where this is located with respect to our inertial reference frame that's pointing east, north, and up. That's what we do in the first step with this attitude Kalman filter. So that's what we figure out here, the orientation of the car. And once we have that, we can figure out the true linear acceleration. So we need to get rid of any acceleration component that is due to the gravity, because our accelerometer just measures this blue vector, and we want to subtract the red one, the gravity vector, which we can do now because we know how our car is oriented. And then we get this linear acceleration, which we can further use to combine with the GPS. So now to the GPS velocity. We need to do one thing with it, because what the GPS tells us is always relative to this north, east, and up-facing reference frame that is attached to our globe. But we want to rotate this data such that it always rotates with the car. Because right now, when we drive a figure 8 in this test, we see that we have no velocity in the z-axis because we did not go up nor down, but we have velocity in the x and y-axis. And we actually want only to know the velocity in the forward direction. So we can't just take only one of these components. Instead, we have to rotate it using the attitude that we previously computed. So once we do this, we actually get a very pretty graph where we see that we only have a component now in the y component. We also notice that we slightly increased the noise and a bunch of offsets in the other axes, which we should actually fine-tune the filters in order to get rid of this. But the general idea is very, very visible, and we see that we now know the forward-facing velocity of the car based on the signal from the GPS. Okay, so with this pre-processing of the signals, we can feed our two Kalman filters. I will not explain the mathematical details of the Kalman filter because I would also have to study this quite a lot more in order to give a very understandable description. But the idea is that that both Kalman filters get inputs. So we have one that records the system attitude and the other one that records the system velocity. For the attitude, we have inputs from the gyroscope. We have the two vectors that I mentioned, the gravity vector and the north vector. And what we get out is an accurate and fused signal for the system attitude. For the velocity, it's actually even simpler because this can be implemented fairly straightforward, since the velocity is a true regular vector where we don't need to consider any edge cases or special cases. So we have as an input the linear acceleration and the velocity from the GPS. And what we get out is an accurate signal for the velocity of the car. Now, let's look at how this looks once we have the system running. So I will show you a few graphs of the outputs of those filters that I just explained. And we will see that the system does actually behave as we intended it to. But we will also notice that the accuracy still can be improved. So the filters do add noise, the filters do add offset, which we need to tweak in order to have the system more reliable and be more accurate. So let's look at the attitude first. I mentioned that I'm representing this using this fancy and actually very, very convenient mathematical construct of a quaternion. So this is slightly unintuitive, which is why I will not explain each component, but we will see that in this test drive that we did here, we were only turning around the z-axis, which is the one that is pointing through the car from the top. So it makes sense that we only turn around the z-axis. The W component actually just ensures that this quaternion always stays of unit length. So that's the specialty about this quaternion, which makes it a little bit more tricky to work with. And what we see as an output from the velocity Kalman filter is the signal that we were hoping for. So we have a smooth velocity in the forward-facing axis of the car in the y-axis. And as I mentioned before, we also do see the offsets in the other axes, which should not be visible unless we have a situation where our car does actually lose traction over the ground, and then we might have a slight velocity in the z or x direction, but otherwise we should not be seeing this. So that actually tells us our system still needs to be improved, even though it does mathematically work as we wanted it to. Just to give you an idea of the error, we tried to compare our system to a black box system that we did not develop ourselves, just to have a feeling of the error. And this graph actually shows the deviation between the velocity vector that we measured and the velocity vector that was measured by our black box comparison. And what we can see is that we are, so on the red figure, or the red line, is the length of this velocity vector, or the difference. And we see that we are usually around 0.5 meters per second off between what the black box measurement system tells us. And the blue line is the angle difference between the two vectors. And we see that this is usually rather small, around 10 or 15 degrees. Unless we get to a situation where we stop the car, then the velocity vector should be 0. And at that point, the angle does not make any sense anymore. So that's why the angle error starts to be anywhere between 0 and 180 degrees once we stop the car. So that's the general idea. And we also designed the system with the idea in mind that we could extend it, because now we have a system that can use inputs from multiple sensors, and we can actually further increase, or we were hoping to further increase the accuracy by properly integrating other data that we can use to estimate and approximate the velocity of the car. So the system is designed to allow for additional sensors as an input, which can be used to make it more accurate or redundant. In general, we have shown that we are able to create a very cost-efficient way a system that can measure the ground speed of a moving vehicle to potentially use it in a self-driving race car. We also noticed that our algorithms still need tweaking and still need some improvement, but overall, we're very happy that we were able to show that mathematically we have the right concept and we figured out how to do it, such that we can now work with our system that is no longer a black box that just some other manufacturer developed, but we actually understand it, so we can keep working with it and tweak it to further improve it. That's the end of my presentation. I am very happy to answer any question. Thank you very much. Yes, please.
How much accuracy would a better IMU add? As I saw it on the photo, choose a very cheap one.
Yes, that is true. So we did not make comparisons between different IMUs. I'm assuming a better IMU will improve the accuracy, but right now we would have to tweak the algorithm first, as I think this is currently the biggest source of inaccuracy. It's not the IMU right now. Once we get to a more refined algorithm, we will be able to benefit from a more accurate IMU. Yes?
Why did you compare the black box to your system and not try to measure some ground truth, some real truth?
So the thing is, we were hoping to get a super expensive sensor to do exactly that, which did not work out in the end. So we had to settle for the next best option to get an idea of how accurate our system was. It's not a very accurate validation that we did. We were not able to do that. So your idea is correct. We would have to get a true measurement of the ground, which is possible with other techniques. but that will have to be done in the future in order to get a better idea of the accuracy. Yes?
That's another question. You showed us that you are using the signals from the IMU and GPS to calculate the velocity.
True.
How does this computed velocity compare to the velocity that we would derive from the IMU alone and from the GPS alone? How much does this adding these two information bring you?
Yeah, so the cool thing is if we just have the GPS usually has a slower frequency of delivering data to us, and we can add more points to this signal by using the IMU. The IMU alone does actually not work because we need a fixed, well, it does work, but we can significantly improve the accuracy if we get a fixed true signal from the GPS at a lower frequency. So that's why we actually combine this. The GPS is very accurate, but we don't get that high of a frequency, which we can compensate with the IMU. That's why we did this. All right. Yes.
Can you tell us something about maybe problems or specialities concerning Kalman filters, maybe instabilities or computing power you need, something like that?
So we did not focus that much on the things we could do by changing the Kalman filter. The thing is we had to implement 2 Kalman filters, and we did not get to compare other filters, so I cannot tell you that much about what problems we might run into there. We had plenty of compute power. We just did not want to limit ourselves in that area. So I would have to do further research in order to give you an answer to that question. Yes?
You also mentioned as an extension an optical sensor.
True.
What kind of sensor would you use? A camera?
I'm actually not sure about how this sensor works. It is some kind of optical technique that is supposedly super accurate, and that's actually what a Formula 1 race car would use to measure its ground speed. That was the thing we were hoping to get in order to compare our system to, but we did not because it was just too expensive. So I would have to look this up on how this sensor works, but there is a proven technique on how to do this with an optical concept.
It's not comparable to a kind of a mouse sensor?
I'm actually not sure. It's not a camera, so that I know, but I don't know which kind of signal is used. I don't know that.
Actually, the mouse sensor is kind of a camera. Yes, the low pixel camera.
All right. If there are no further questions, I think I wish you a happy lunch, and I will be downstairs also to discuss if there are some questions that come up. Thank you very much.